All right, so for the past couple days, we've been talking about ionic compounds and how we start to name ionic substances. Now remember, in order to have an ionic compound, you gotta have two things. You gotta have a metal and a non-metal joined together, transfers an electron, the metal gives it to the non-metal, makes a cation and an anion. These electrostatic charges stick us together. So now we can start to name these resulting groups. And now there's two rules, two big rules when we start looking at ionic nomenclature. First one is the charge must be zero. Any ionic compound, in order to be stable, has to have a final charge of zero. Okay? Charges have to balance. Second rule is that the metal always comes first. On our periodic table, as we look from left to right on the periodic table, we notice the metals always come first. It's a real nice way to tell, are we ionic or covalent? If we look at the first element, we go, oh, metal, ionic. We can name it accordingly. So, if we were to come to our handy-dandy example here, magnesium chloride, we start by writing the symbols for the elements represented by the name. Magnesium, if we look at the periodic table, has a symbol Mg. Chloride, ide, meaning chlorine, we change the ending to ene. Chlorine is Cl. Now, if we look at the periodic table, find magnesium, we find it in the second family of the periodic table, or the alkaline earth metals, which means it has two valence electrons. To become stable, it's going to give those two away, giving it a 2 plus charge. A 2 plus charge. Our chlorine, in the seventh column on the periodic table, or the halogen group, has 7 valence electrons. It's going to gain 1, giving each chlorine here a 1 minus charge in its ion form, in its anion state. Now, if we look, we got our metal first, we're good, but our charges do not balance zero. Now, there's two ways we can think about this. Either we can add a second chloride ion, making 2 chlorines. We would show that with a little 2 here. And so MgCl2, we can look, okay, how can we make our charges be zero? Or there's another way. We call it the crossover method. If you start by finding your charges, magnesium is a 2 plus, chlorine is a 1 minus, what we can do is we can take the number and just cross them down. Mg with the 2, the number, just the 2, comes down to the chlorine. The 1 comes down to magnesium. Well, the nice part is magnesium it's an implied one. You don't have to write it if you don't want to. Now do make sure whenever you write these compounds, go back and clean it up. Clean it up, because now the charges are neutral. They balance each other out. Our final compound then, when written in its formula unit, would be MgCl2. Let's try the second one. Calcium hydroxide. Calcium, go to the periodic table. Ca. Cool, got it. Hydroxide, we go to the periodic table. There's no hydroxide on the periodic table. That's because it's one of our special groups, our polyatomic anions. One of our polyatomic groups. It's a covalently bonded charged particle, which then can bond ionically with something else, in this case, a calcium. All right, now, if you forget, if you don't remember your polyatomics, check the back of your periodic table, your yellow periodic table. Ooh, what's that? So on the back of your periodic table, you will find, blammo, a huge list of all these ions, lest you forget what their charge or formula might be. Now, this is great for homeworks. You're not going to have this for quizzes. You're just going to have this guy. So we'll get those learned as we go here. But great tool for us as we start learning some of our naming systems. So we go hydroxide, hydroxide, hydroxide. There it is. It is OH with a charge of a 1 minus. And we can just put a dash for a minus. We go to the periodic table. We find calcium. Find calcium. It is in that second family on the periodic table, meaning it's going to have a charge of 2 plus in its cation form. 2 plus in its cation form. Cool. We're done. No metals first. We're good. But the overall charge is not zero. So we got to get these stable. So what we're going to do is we're going to go ahead. We'll just take the numbers, cross them down. We said this is a 1 minus charge. We bring the 1 down. We don't have to write it. It's implied. Right? You want to write it, you can. When we get to the point where we don't need those so much anymore. But if you want to write it, you can. We take the 2, cross the 2 down. Now, if we left it just like this, we'd be in trouble, because this is not saying 2 hydroxides. This is saying 2 hydrogens. Whenever we have more than 1 polyatomic ion, polyatomic meaning many atomed ion, we're going to go ahead, put the whole thing in parentheses. Put the whole thing in parentheses. This means that that 2 now distributes to the O and the H. We have 2 of this entire block. If you want to think of it like a Lego block, that's fine. It's OH is 1 4 square Lego block. If we gotta change the charge, we're gonna put in a 2 in there. Now what this means is that we've got 2 OHs, each one with the 1 minus charge. That's gonna balance the 2 plus from the calcium. Remember, our overall charge gotta be the big old goose egg. Gotta be 0. Cool. Let's try one more. Cu copper 2 oxide. All right, head on over to the periodic table. So I'll just that way. Head on over to the periodic table, you find copper. Sweet. Cu oxide. Oxide. Oxide-ide meaning, oxygen. Gets the big old O. Find oxygen periodic table. Has 6 valence electrons. Gonna need 2 more, so it's gonna have a 2 minus charge. Find copper on the periodic table. What charge is it gonna have? Oh no, it's in the middle, which means it can change its charge. Bomber. Shoot, well, maybe there's a way we could figure out what the charge is based on the name. Well, the 2 minus came from the oxygen from the periodic table. That 2 is going to tell us what the charge on that copper is. Cu2. Copper has a 2 plus charge. Now, we could use the crisscross method. 2 plus, 2 minus, cross them down, be stable. But really, if this is a 2 plus and this is a 2 minus, wouldn't one of each balance each other out? Yeah. We are stable. So this is how we can go from the name to the formulas. Always put your metal first, check your charges, make your charges 0, and you're done. Now, let's go in reverse. Reverse. We're going to flip it back the other way. Let's say we've got the formula, but now we need the name. Okay, all right, we're doing okay. So start by naming your first cation. Always start by naming that first element. We're just going to name it what it is. Find Be on the periodic table. We find, let me see here real quick. This usually takes longer than actually writing it, so we'll get better. Be, there it is. Be is Beryllium. Beryllium. Name the first element just like normal. Just calls them like you sees them. What is the name? Now the second element, you'll notice we changed just a little bit. Notice here, the second element's ending changed to ide. This tells us that we have an ion. That's a charged particle, and as an ion, it's going to go ahead and bond ionically with other elements. So we go ahead, Br, on the periodic table. Br is bromine. We're going to change the ending to bromide. So the total name here for BeBr2 is beryllium bromide. Now you notice we didn't put Roman numerals in here, did we? We didn't need to, because when we look at beryllium, we notice it's in the second column on the periodic table. And since it's in the second column, it will always have the same charge. It's always a 2 plus. The only time we need Roman numerals is if we're talking about any of our transition elements or our post-transition elements. That's when we use Roman numerals. If it's one of these first two, don't need to worry about those Roman numerals. They will take care of themselves. We always know their charges. All right, let's try another one. SnO2. Sn, go to periodic table. It is tin. I know. Tin does not abbreviate to Sn. Blame it on the original Latin. Tin. Sn. Tin is a post-transition element over here. And it's tricky because it'll change its charge. So we need to figure out what the charge is to put it in the name. So we know we're going to need Roman numerals. It is a transition or post-transition element. We'll leave that blank for right now. We'll come back to that in a second. Let's check out our ending. Oxygen has the ending oxide. We change the ending to ide, I-D-E. Oxide. Oxide. All right, well, let's check out oxygen. Find oxygen on the periodic table. Find it. It's got a set charge. It's always got a -2 charge. But we've got 2 of them. We got two negative charges for a total of 4 minus. Well, if we got a total of 4 minus, what would the charge on this one tin have to be to balance it out? We got 4 negatives. We'd have to have 4 positives to balance it out. Charge on this tin would be 4 plus. Now, how do you show 4 in Roman numerals? That would be IV. Not like the green leafy stuff, poison ivy. Not so good. IV. I with a V following. Now there's one time when we don't change the ending to "ide," and that's one of our special groups. We've been working on memorizing those: so phosphate, sulfate, carbonate, nitrate, hydroxide, acetate, ammonia. These are our special groups, right? If we have one of those special groups in our compound, for example, let's say we had CaNO3 parentheses 2. We always start by naming the first element just as it is. In this case, Ca would be calcium. NO3 is one of our special groups. You're not going to find NO3 on the periodic table in its entirety. It's a special polyatomic ion. That's why we got to memorize these. Very important we memorize these so that we can recognize them when we see them. NO3 is a special group called nitrate. We don't change the ending. We just call it nitrate. Now, calcium, nitrate. Do we need Roman numerals for calcium? Transition element? No. No Roman numerals. It is perfect, just as we have it written here. Okay? So now we should be able to go from names to formulas, or formulas to names. If you need to see the examples again, feel free to replay the video. Otherwise, go ahead, give a couple problems a shot for me.